Okay, so for today, we are going to be taking notes over equilibrium. So, for equilibrium, first thing we want to do is remember and define what an equilibrium reaction is. An equilibrium reaction is any reaction that can run both forwards and backwards. And we talked about this before with your lab. Forwards, again, being that standard direction reactant to products. Backwards, or reverse, being the opposite, running from products and actually making reactants. So, equilibrium, anything that can go both forwards and backwards. Now, we're going to walk through an example. Our example today is going to be carbon dioxide, dissolving in water. Now, the reason I picked this example, this is what is going on in the oceans. CO2 gas is being released into the air by smoke, fossil fuel emissions, car exhaust, and that CO2 gas has to go somewhere. And one of the places that is going is into the ocean. And when it hits the ocean, it's actually reacting with the water in the ocean. So when we take that CO2 and we mix it with ocean water, we get a slightly more acidic ocean because we form the acid carbonic acid. Now, this is not permanent. This reaction is temporary. The rate of CO2 dissolving into the ocean is changeable, and we can change that by changing environmental factors. So when we have a change in the environment, or when we have changes in the environment, we can cause changes in the reaction. And changes in the environment can be similar to what we've talked about before. We could have a changing temperature, or we could have a changing pressure. Now, for this specific example, we're going to look at changing temperature. So we're going to take the same example, and we're going to heat it up. Carbonic acid is heated. Now, when we take that carbonic acid and we heat it, it's going to decompose and break down, releasing that CO2 and reforming that neutral water. Now, you should notice something. These are the exact same reactions. Chemically, they're the same chemicals. We have CO2 and water on one side, and we have carbonic acid on the other. So they're the same reaction, just reversed. This reversibility is what makes this an equilibrium reaction. So what we can do is we can rewrite this in a proper equilibrium form. For an equilibrium reaction, we're not going to write it twice. That's redundant. We're going to write it one time. But but we're going to use a double arrow. So we're going to start with CO2 and water. And like we covered in the first half, CO2 and water mix together to form carbonic acid. Carbonic acid, however, can also break down and form CO2 and water. So we have this equilibrium arrow that shows that reversibility. And this is always happening. This is occurring in the oceans constantly. Both ways. So the ocean is always both absorbing CO2 and making carbonic acid. That carbonic acid is always breaking down and releasing and forming those CO2s. So both parts of this equilibrium reaction are always happening. When they happen at the same rate, this is called the equilibrium point. So that's something we definitely want to understand. Both forward and backward are always happening. When they happen at the same rate, this is what we call the equilibrium point. Now, this equilibrium point is not a set point. Just like we can change a reaction by adding a stressor such as heat, we can also change the equilibrium point. Using similar factors. We can change the temperature, we can change the pressure, or we can change the actual amount of chemical that we're using. Now, when you were changing the amount of chemical though, you're only changing the amount of chemicals you already have. You're not introducing new ones. So we might take this reaction and add more CO2. Or we might take this reaction and add more carbonic acid. But we're not going to take this reaction and add sodium. We're not going to introduce a new variable. We're just going to play with the amount for the variables that we already have. So this is equilibrium in a nutshell. What you should have an understanding of is equilibrium is a type of chemical reaction. Specifically, it's a chemical reaction that can go both forwards and backwards. The example we covered today is the equilibrium reaction that occurs in the ocean. Water can absorb CO2 and form carbonic acid. Carbonic acid can also break down, releasing CO2 and water as it forms. Because we have both reactions, we can put them together in equilibrium format using that double arrow. Remember, this is the ocean equilibrium reaction. You're going to need that later in your worksheet. Both the forwards and the backwards are always happening, and then when they occur at the same rate, this is the equilibrium point. We can change that point by changing some variables: temp, pressure, and amount. Your lab? Just put it in the tray. You're okay. All right, so that's equilibrium, the basics. Now we're going to get into equilibrium, the specifics. So go ahead, turn the page in your packet. Should just be another blank page. But now we're going to look at examples of this bottom section. What happens specifically when I change the amount of a chemical. For this page, we're going to run 4 different scenarios, but they're all going to be about the same parent reaction. Our parent reaction is going to be copper reacting with aluminum chloride to form aluminum and copper chloride. Since this is an equilibrium reaction, this also means aluminum is capable of reacting with copper chloride to form copper and aluminum chloride. So this is my parent reaction. My whole page is about this reaction. We're not going to use any different chemicals, but we are going to add some different stressors. Stressor number 1. We are going to add copper to a reaction, or to the reaction previously in equilibrium. Equilibrium is all about balance. So to help us understand how this is going to change the dynamics of the reaction, we're going to use a model that's all about balance. We're going to use a teeter-totter. Now, because this reaction was previously in equilibrium, my reaction started balanced. So I'm going to start my teeter-totter off nice and flat. Got my pivot in the middle, and I'm going to put 2 boxes on the left to represent my 2 reactants and the rate at which we're forming reactants, and then I'm going to put 2 boxes on the right, and these are going to represent my 2 products and the rate at which we're forming products. Now I'm gonna add the stressor and see how this impacts my teeter-totter. I am adding copper. When I look up at my equation, as it's written, copper is a reactant. So when I redraw this teeter-totter, instead of 2 reactant boxes, I'm now going to have 3 because I'm adding copper. So I'm going to add that stressor, and now I have 3 reactant boxes on my left, but my products didn't change. I only have 2 units on my product side. So that's going to shift my teeter-totter. If I have more on the left than I do on the right, that left is going to drop because, like a teeter-totter, the heavier side drops. And the right is going to be elevated. This gives my teeter-totter a directionality. My teeter-totter is pointing to the right. Your teeter-totter, your arrow is always going to point up. And from this model, I can figure out exactly how my reaction is changing. To figure this out, we break this up into 3 components: cause, effect, and result. So my cause here, what I did was add copper. Copper being a reactant. And what I did here was I shifted my teeter-totter, and my teeter-totter is moving this way now, up and to the right being forward. So my forward reaction is going to increase. Because my forward reaction is increasing, my equilibrium point has shifted, but reactions will find a new point. If I wanted to get an even teeter-totter again, what I'd need to do is put some more weight on the right, which means I would need to make more products. Okay? 2 ways you can think about the right. Think about, how would I rebalance the teeter-totter? What would I add more of? Well, I would need to add more products. That would balance the teeter-totter. Or you can just think about the arrow. My arrow is pointing to the right. That's the product side. I need to make more products. But either way, this model gets you to your answer. This is what the problem types look like for equilibrium. I give you a stressor. and an equation. Given a stressor, you should be able to identify the cause, effect, and result of that stressor. What's causing the change, which reaction is going to increase, and what's the result of that change? What am I going to make more of? So we're going to do the same thing, but we're going to do a new stressor. For my second stressor, this time I'm going to remove something. I'm going to remove copper. And the second part of the prompt is always true. It's always going to be from the reaction previously in equilibrium. I'm not going to write that every time. We know that this is our reaction. We know it naturally exists in this nice balanced state. So, since it was the same given, nice balanced state, my teeter-totter is going to start nice and balanced. 2 of each. Reactants, products. Now, this time, my change is different. I'm still dealing with copper, which is a reactant. So I'm still working on the reactant side. But this time, copper is being removed, which means instead of adding an additional box on the left, I'm going to take a box away. So now my left is only going to have 1 box, and my right is going to have 2. So my teeter-totter is going to look more like this. And now if I wanted to climb up the teeter-totter, I'm going to be climbing to the left. And from here, I can identify how my reaction is going to change. Cause is just rewording your stressor. Copper is removed. Copper is on the left side, so it's a reactant. So my cause here is going to be reactant removed. My effect here, now my arrow's going the other way. My arrow's not going forward, my arrow's going backwards. So now my reverse reaction increases. Which means if I want to rebalance this, which equilibrium reactions want to find that point of balance, what I need is more reactants. I need to make more reactant. And you can also think of that as, where's the arrow pointing? To the left. What side is the left? That's the reactant side. But either way gets you to the same conclusion. Anytime we have a reactant removal, we have a scenario that actually makes more reactants, which makes sense. It wants to reach a state of balance. If you remove something, you're going to rebalance it by making more of that thing. All right. Stressor number 3. For stressor number 3, we are going to have aluminum being added. And we know now we're always going to start in the same spot. Teeter-totter. Reaction rates nice and balanced. 2 boxes of each. All right, and I'm going to stress the teeter-totter out. Now, dealing with aluminum. So back up to my parent equation. Finding aluminum. Now, this is aluminum chloride that's different. Aluminum is just aluminum. This time, I'm dealing with the product side. So I'm going to be messing with my blue boxes. And what am I doing to aluminum? I'm adding it. So now when I redraw my teeter-totter, I have added a blue box. Which means that right side is heavier, because I've got 3 over here. And 2 over here. And if I'm going to climb up the teeter-totter, where am I going? Well, I'm headed to the left. Okay, so getting those teeter-totters down should be easy, and we should be getting good at cause, effect, and result by now. So this time, my cause. What did I do? Well, I added something. What did I add? Added on the right, that's my product. I added a product. What's my effect? Well, again, look at the direction we're going. We're going backwards. We're going in the reverse. So my reverse reaction is going to increase. And what's my result? Well, if I want to rebalance this thing, I need more on the left. I need to make more reactant. When you are looking at the result, you're always going to be looking at what can I add? What can I make more of? We're never going to look from an angle of lesser. So what can I add? I can add reactant. Need more pink. Okay. All right, so if you remember, I said there are 4 scenarios. This means we are on our final one. Stressor number 4. For stressor number 4, we are going to have copper 2 chloride. Which is the formula CuCl2 being removed. So, starting at baseline, identifying reactant and product, reactant on the left, product on the right. And then figuring out what is my specific stressor. So going up to my parent equation, copper 2 chloride. CuCl2 is a product, and my prompt says I'm removing it. So I'm taking away a product box, which means I am taking away a blue box. So I'm going to have 2 on the left, 1 on the right, which means I am heavier on the left. Okay, teeter-totter, if I wanted to climb it, climbing up, going this way. And now I can identify my outcomes for my cause, get my effect, and my net result. So what did I do here? This time I removed. What did I remove? I removed a product. What was my effect? We'll look at my arrow. Which way am I going to have to move in order to rebalance? I'm going to have to move forward. So my forward reaction rate is going to increase. And what's my result here? Well, if I wanted to balance this teeter-totter out, what would I need to do? I need more over here. I need to make more reactant. Sorry, make more product. Okay. Now, this covers the 4 chemical stressors. The 4 chemical stressors, any given cause always produces the same effect and result. Doesn't matter if it's this equation or a different equation. Anytime you're removing a product, the effect and result are always going to be the same. I'm going to increase the forward and I'm going to make more product. Anytime you're adding a product, effect is always reverse reaction increases. Result is always make more reactant. Now, these are very predictable stressors. Making this change always results in these outcomes. Our other stressors are a little bit less predictable, such as temperature and pressure. They are important, and we're going to look at a virtual lab that talks about them more, but they are less predictable. One given cause will not always give the same effect and result for a reaction. It depends on the specifics of the reaction, but they still can affect an equilibrium point. We just don't do sample problems with it here because it's not quite as generic. It's more specific. So you would be looking at specific problems, and you'll do that in your virtual lab.